Okay, so hello everyone. This is Takashi Shida, and I am a lecturer at the University of Tokyo and visiting scientist at RIKEN AIP. And we have been hosting TrustML Young Scientist Seminars, or TrustML YSS, which is a seminar series that features young scientists giving talks and discoveries in relation with trustworthy machine learning, led by Jing Feng. And today is the 63rd seminar, and I am excited to have Mimee Xu. Mimee Xu is a PhD student in New York University, advised by Leon Batu, with a focus on AI privacy. Her previous work explored secure and equitable evaluation of privacy training data for machine learning. Today, Mimee will give us a talk about Netflix and Forget, which is her recent work about machine unlearning. So Mimee, we are very excited to learn about your research. And if you're ready, please begin.
And thank you so much for having me. I'm a PhD student in New York University. My work is mostly on the intersection of machine learning and privacy. I'm a fifth-year PhD student. Today, I'm going to be talking about Netflix and Forget. Specifically, this is about finding an efficient and exact machine learning solution from bilinear recommendations. Now, this talk is going to be very much motivated by real-world scenarios. So it's going to be divided into 4 parts. First, it's about this particular privacy context of consumer technology, in our case, Netflix. And then in this very messy real-world scenario, we're going to find out what we could define mathematically with respect to machine learning. And then I'm going to be introducing our solution called Unlearn ALS, and this will include the results and the simulations. And lastly, I would like to touch a bit on where unlearning can go, coming back into the real world. And there will be questions between slides between these sections. So I'll start from understanding the need to have unlearning methods. Ever since 2005, I think most machine learning researchers here have heard of the Netflix prize. This is about the type of data where we have users and the movies they have watched and the ratings they have given to the movies. And since then, machine learning-based recommendations have become a ubiquitous technology. This is the type of machine learning and AI that's not tomorrow. This is right now. It's been around for a really long time. Users are used to it. This type of recommendation is special in that the users kind of consented to having their histories and ratings recorded in return for this type of service where they interact with this recommendation engine. People actually browse Netflix front page for 45 minutes before they decide on what to watch. So there's this reflective loop to the data we give it to the system and what we're getting back. And there's an implicit contract between me and the platform. What's also special about Netflix is that Netflix is usually a social activity. Even though the account is owned by one person, people in relationships, for instance, often watch things together as they spend time. And today we're talking about exactly this type of scenario. So we consider a couple streaming Netflix shows on a couch. Together, their watch history is fed to the recommender, and in turn, Netflix gives them back the shows that they think that they will enjoy watching together. But the real world is complicated. Sometimes couples break up. So let's look at this scenario. After a heartbreak, the watch history that the couple had generated remains the same. As far as the recommendation engine is concerned, the watch history has not changed. Their preference has not changed. So it will recommend the same movies and shows. Now we consider this newly broken up user browsing Netflix using the same account. What will he see? Upon opening Netflix, he is bombarded with new notification alerts for the episodes coming up for this show that he and his ex-partner failed to finish. He scrolls down, he suggested these movies and shows that feature the exact same actors. And say the couple used to watch, say, Korean drama, romantic comedy. This subgenre is quickly identified by most recommendation engines as international romance, and this subgenre will be surfaced as an entire row of international romance movies and shows for him to watch. Now, this naturally gives him some form of distress, a discomfort. Even though he agreed for that data to be released to Netflix initially, he now doesn't quite want it. This is a common scenario where the downstream recommendations take a really long time to update. But when users are interacting with the recommendation engines, these recommendations haunt users by reminding them of their losses. In this scenario, it will be very natural for our user to ask Netflix to please remove all watch history of Korean dramas from my Netflix. Now let's unpack that for a moment. What does he mean by this removal? He's not only talking about removing the list entries. If you go to your page or watch history, he wants those entries disappeared. He's really talking about this interaction with recommendations that he's getting back. He would like this change of removing watch history to be reflected in his future recommendations, so he could carve a new path forward. So when we talk about machine unlearning in my talk, I'm specifically interested in the scenario where the users previously consented in exchange for the services, their preferences are, however, not continuous and may change abruptly. And this happens all the time. Another example is this bereaved mother who suffers a miscarriage. She loses the baby and she's haunted by Facebook ads that keep telling her to buy baby goods. She is sad, she's angry, and she's confused why Facebook doesn't recognize that she has lost her baby. Because after all, she says that she has written a really long Facebook post detailing the whole experience. But these systems are very common, right? Even if they receive new information, all of these past recommendations, preferences tend to be very sticky. This is what privacy scholars call decontextualized freshness, a common problem with today's machine learning systems, because this data that we generate in the past is resurfaced. The things I was browsing a month ago, I will be reminded to check out even today. This becomes a problem, especially during breakups, miscarriage, but there are also examples of bereavement. When people lose loved ones, they're reminded of happy family time through memories, or someone who has had a traumatizing experience, such as becoming a victim of crime. These recommendation interfaces may in turn become triggers. So here we're only talking about the need in the real world to have machine learning, even if not coming from a privacy perspective. And that concludes the first part of my talk. Other questions?
Please feel free to ask questions either by unmuting yourself, or you can also use the chat box.
Okay, I'll move on to the next part, that is to define unlearning. So the real world has many different modes and scenarios. It's impossible to cover all of them. So we're going to be focusing on the specific Netflix example. In that example, our goal for unlearning is to unlearn user-selected historical records from existing recommendations so that the downstream recommendations proceed as if they were not trained on the selected data. Now, this is a lot, and we're going to be defining all of the terms involved. First, what are the existing recommendations? For the sake of this talk, I'm going to be assuming that the existing recommendations are the ones already deployed, and they will be bilinear recommendation models based on matrix completion. And they were a pretty major part of most of the solutions to the Netflix challenge. And even as today's recommendation engines become more and more complex, the bilinear models still serve as a good basis where different variants are developed. And after all, we would like to understand this unlearning problem from the most basic type of models, and that would be the bilinear models. Next, we talk about what are the user-selected historical records. Obviously, given all the data we have observed, users will select a subset of the existing observations to remove. And this subset is likely going to be very, very small compared to the entire data set. And for the rest of my work, I'm going to be modeling those historical records as uniformly distributed because we don't know which records will be deleted. In reality, if you imagine this being a thing, right? If users were to submit deletion requests after a breakup, they probably tend to delete romantic genres. And after some political, informed boycott, maybe some specific film director will see a lot of deletion requests. So it might not necessarily be uniformly distributed, but for now, we're assuming that this is IID DROM. Next, it comes to the meat of our definition. What does it mean when we say deletion, right? This subset has to be deleted from both historical records and future recommendations. Implied here is this pretension that after whatever our procedure of unlearning is, the resulting recommendation model needs to act as if that removal data set was not included in the training set. And this looks awfully close to retraining, right? If we didn't see that data in the first place and we were to retrain from scratch. So naturally, we're proposing a baseline in our definition, and that is retraining the model on the remaining data set and the remaining data set only. Now I want to ask the audience this strawman question. Why don't we just remove the whole category for this user forever? Right? If we're about to surface some item, we just check if it is part of Korean drama, and if it is, we just don't show user this category. Do you see potential problems with this implementation? So, if we were to remove the entire category for the user, the big problem I'm interested in is model utility may be hurt. And by that, I mean, it could be an over deletion or it could be an under deletion. Imagine if only Korean drama were to be removed for this user, there could still be, say, Japanese romantic drama such as First Love being shown when the user really doesn't want to see anything romantic recommended to him. Another example would be this really famous Korean drama called Crash Landing on You. During the COVID-19 lockdown, people all over the globe who have never been exposed to Korean drama before actually enjoyed this show tremendously. It became one of the most popular shows. And if this is conspicuously missing from the recommendations, it actually poses further privacy problems and also hurts model utility because we're not recommending him really good shows. Instead, we're excluding them. So our definition needs to come with some restrictions. First, we would like to maximize model utility. And in my work, this is paramount because if the model utility is hurt in any way, I just assume that industry has no incentive in adopting whatever unlearning mechanism we have. Next, it needs to be swift because retraining from scratch is quite expensive. So we want a method that minimizes computational costs. The third and the fourth points are about this type of deletion. We want to have the guardrail to avoid over deletion, and we like to be complete. Like it cannot just remove a little bit of influence. We want it to remove as much as possible. Overall, we want our deletion to really emulate the effect of retraining without having to go through the computational cost of retraining. And this set of goals is consistent with the usual machine learning literature's goals of trading off accuracy, speed, computation, and privacy. And here I'm simply ranking them and explicitly talking about them. Specifically, we would like to preserve model utility while removing the influence of a subset of data. We want our removal to be swift so that we avoid the time-consuming nature of retraining. And we also want it to be complete and calibrated. This part of our definition naturally needs some models. On the left, we see these data sets corresponding to the models. So the original model that we start with will be called undeleted model, and that is trained from scratch from all the observational data. And then we have the retraining model that is trained on the remaining data. Lastly, we have our on-training procedure that has seen the observational data and is also given the user requested deletion, the removal data, and it needs to come out with this final model after on-training. The recommendation itself will be based on matrix completion. We're giving a dataset P that is a partial observation of preference matrix M that represents a ground truth of users' preference over an item. And since most people have not watched most movies, P really has very few explicit observations compared to the size of M. We assume that M is in fact low rank for user and item features X and Y. The users will select watch history, remove a dataset, draw IID from all the observations. And that concludes our assumptions. Specifically, these models will be used as baseline. The original model will be the baseline for our performance because we don't want to have any model degradation. We would like the model to now be much less useful than the undeleted model. And then we want a retrain model as a baseline for privacy loss. We would like to emulate the privacy level of a retrained model as much as possible, even if the untrained model has had access to the observational data. Specifically, the model utility will be evaluated on the AUC of model on the held out test sets, and the model's privacy will be evaluated using membership inference attack accuracies that will go into details into the future. And this concludes our definition for learning, and I'll be taking questions regarding this section.
Can you go to page 22? So M untrained has a bit more access compared to M retrained.
Yes.
I see.
Yeah.
So
we're
for
talking on-training method that has access to all of these. So after on-training, you can't really make the point that the model has never seen it before, right? As opposed to retraining where the model really has never seen the removal data.
I see.
Yeah,
Okay.
so we're trying to approximate.
Thank you very much.
Yeah. Yeah, this particular difference is relevant in a lot of legal literature, such as how copyright is defined in the United States. We can't just approximate the model. We have to really show that the model never had access to that data. So here we're talking about this approximation mainly in the numerical sense.
Okay, I see. Thank you.
Other questions? Okay. Next, I'll be talking about our proposed solution. But before that, we'd like to dive a little bit more into the baselines. Recall that we have these models used as baselines, and both of the undeleted model and the retrain model are training from scratch, right? So we really need to decide what we're using to do the training. And for the rest of my talk, for now, I'm going to be assuming a particular type of optimization being used. And this is alternating least squares. The summary of alternating least squares is that it's a regularized matrix completion method with parameter lambda. We have our explicit observations collected in this matrix P. And we're using this observation set to denote the set of coordinates where we actually have seen user watching movie and giving feedback. For all the missing data, and that is most of the entries, they're assumed to be 0 in matrix P. The specific method we're using is called implicit feedback, in that it especially includes a soft copy of ratings as matrix C, and it heuristically associates each entry with a confidence score CUI, and you can see that in the form of the loss function. We don't need to worry too much about this soft copy of ratings matrix because they're mostly fixed from the beginning. It doesn't get updated throughout the optimization method. You can kind of think of it as a way to smooth out some uncertainty we have regarding missing data. Because if we assume missing data to be lowly rated or highly rated, that would be inappropriate, right? So we want something that's a softer, that kind of heuristically denote our uncertainty with those values. This method looks a little bit arbitrary. It was first proposed in 2008, and ever since this paper, it has become widely deployed. The method itself is highly parallelizable, and it has a lot of really nice empirical properties, such as being very fast converging. It's also very simple to implement. As you can see on the right, this is a very simple algorithm, and it's called alternating least squares because in the while loop, it's alternating between updating the user features and the item features. And each one of those updates, it's a least squares problem, which makes it very convex. And it has become the default in most of the machine learning libraries. For instance, if you were to do collaborative filtering based on machine learning using SparkML, this is the underlying implementation that it will be using. It's fair to say that if people were to put out a new recommendation product, chances are it's based on something very close to what we have right here. The bad part about assuming alternating least squares is that there's little theoretic guarantee associated with this method as is. There are many variants proposed so that they have better theoretic guarantees, but they're not as widely deployed, right? So we're working with this fast but popular heuristic. Our on-training is defined very similar to alternating least squares, and I'll be putting the algorithm side by side. As you can see here, the bulk of these two algorithms are pretty much the same, meaning the iterative training steps are exactly the same. It's still alternating least squares. The difference is that on-training will start with the trained feature, so it's got that warm start, pre-training happening, but it alters the intermediate values associated with the removal set. First, we see the PUI for the removal data set being set to 0. This is very natural because we said that missing data is noted as 0 in matrix P. So once we remove that data, it obviously becomes missing data, so it should be 0. And the next thing, which is a little strange here, is that we set that intermediate confidence matrix entries to 0 if it's part of the removal set. I'm going to tell you that this has the effect of blocking the influence from the removal set to the rest of the optimization. But if you just look at this picture, you see that it's kind of an architectural hack, right? It seems a little bit random, and you don't have to know much more than that. This is something I'm doing that's surgically changing some part of this alternating least squares specific optimization. Just to reiterate, there are only 3 differences that our on-training algorithm has with training from scratch. That is, it starts with pre-trained model, and it gets to remove the removal data from further training, from the training data itself. And next, it blocks the removal data from intermediate influence for the rest of the optimization. And what happens now? Right. For the results, I'm going to be talking about the theoretic and the intuitions that we already understand, and then I'll be talking about the simulations. And I'm going to start with the speed. When you look at these two algorithms, it's very clear that because the iterated steps are the same, given that if we're doing both training and on-training on the same data sets, the dimensions will be the same, meaning that every single pass of retraining will take the same amount of time as on-training. And the next part of this intuition is that having had that warm start helps on-training to have faster convergence because it's already starting from a place of very low loss, right? So we will assume it doesn't take as long to converge compared to retraining. Another benefit from having such a similar algorithm is that there's like a very rich set of literature regarding analyzing alternating least squares because they're so effective empirically. People want to know what exactly is going on. So that set of literature mostly will apply to on-training as well. And there are more details on this in the paper. Next, I'll be talking about accuracy. So after the surgical change, we arrive at these three loss functions with respect to the three models. So first, it's just a functional form of training with alternating least squares. When we retrain, we simply swap the data set, that is all the observational data points with the remaining data point, and everything else stays the same. And that's how you arrive at the second equation. For the third equation, on-training again takes into both the full data set and also the removal data set. Assuming that we have already zeroed the P matrix entries associated with the removal data, we are just using this FC function to denote the transformation on the confidence score, so that it remains the same if it was not part of removal and is 0 if it's part of removal. Those are just a functional form. I'm going to be showing that on-training will achieve the same loss as retraining. So after we expand this third equation, the right-hand side, by the different data sets, and then we plug in the zeroing that we're doing on the confidence matrix, we'll see that all the entries associated with the removal data the users have requested to remove is zeroed, meaning that we have this functional form of on-training loss being equal to retraining loss. And what does that mean? It means that through this little hack of setting the confidence to 0 in alternating least squares, we have this algorithm that's functionally equivalent to retraining with ALS, right? This means that if we have two parallel pipelines, and one is doing retraining and the other is doing on-training, and both arrive at minimal loss, that they will actually arrive at the same loss, right? That's all it's saying. It means that if retraining were to beat our ground truth of, say, model utility, then on-training can achieve the same loss. And this is a very strong result because it's implying that we actually don't need to have any model degradation, that we could potentially do exact deletion. We don't have to approximately delete things. And if we do this several times, maybe it'll degrade the model. We don't have that worry, potentially. And we'll verify that through our empirical evaluations. A big remark on this is that whether or not that minimal loss is achieved, for instance, when we're training, we typically have early stop, right? We have regularization. So whether the solutions at that minimal loss are necessarily equivalent or even equivalent up to a rotation because it's, matrix factorization, that's not guaranteed from this analysis because we don't have uniqueness results associated with a heuristic that is alternating least squares. All we can talk about is that they achieve the same loss functionally. We can't just say we're finished, like everything is good. We still have to evaluate privacy. So privacy is pretty tricky to show because even if our model performs the same way as the retrained model, we cannot be sure that they have the same privacy because even if the aggregate losses are the same, we don't really know if they'll output the same recommendations or if one necessarily memorizes more than the other, because our on-training has seen the removal data after all. My point here is really that privacy inherently needs a perspective that includes the concept of an adversary. Say, if someone's looking over your shoulder, examining your recommendations, could they potentially figure out what was deleted? Right. Again, we're not motivating the whole thing from a strict privacy adversary perspective, but for this part of the evaluation, to see that we have really removed the influence of the data users want to remove, we want to look at this privacy concept and use that for evaluation. This brings me to the concept of membership inference. Membership inference is a very popular empirical evaluation for privacy with respect to training data. The formulation is typically it takes a model and outputs a range from 0 to 1 to measure how much a given model memorizes some training data. And the assumptions we want to make is that if an adversary had access to all the user features, all the removal data, and all the remaining data, could it potentially have a good guess just from model output whether or not some data was in the removal set? And for that, we set up a binary logistic regression to only observe the model output on given data and try to classify on the hot set whether that unobserved data point was part of training. Specifically, we want to show that the result of membership inference on the untrained model approximates that of the retrained model. I would like to note that instead of just using the raw accuracy on one model, we're interested in the difference, because the retrained model, even though it has never seen the deleted data points, it may still have non-zero membership inference accuracy under this setup, because there might be some good guesswork. Some data points might be correlated because this is the real world and where the nature of the problem itself, right? So we're more interested in the difference. Like, is untraining really similar to the vulnerability of retraining? Now this is the second part of our method section. It's about experiments and numerical simulations. We're using the data released by Netflix in the Netflix challenge, and it's called MovieLearn. First, we examine the fit using untraining. We see that from top to bottom, as we continue to untrain, it converges quite fast, right? It converges in 10 iterations. Normally, if you were to retrain, it would take about 45 iterations. So untraining is quite a lot faster, and this is replicable in all the sizes of data sets. And this is a subtle point. If we were to keep our untraining algorithm running, what happens? We see that it doesn't really overfit, and it doesn't really have model degradation. So this is one of those safe methods that you can keep running. You don't really have to know the exact hyperparameter you need to use. Next, we talk about privacy, and this is our membership inference results. Again, from top to bottom, as we are doing more and more training, we see that the retraining vulnerability and the untraining vulnerability are getting really, really close. On the right-hand side, it's a slightly different metric. It's looking at the accuracy change from original to the undeleted model, and it's on the bigger data set. It is still visible that we see that as training goes on, that the vulnerabilities of untraining and retraining are approximating each other. But it's becoming much less sensitive. You can see numerically that that number is really, really small, and that the range where it is obvious visually, it's a very specific removal fraction. And this is one of the big problems with our setup of membership inference, that is, it really doesn't scale very well. On that topic, I'd like to mention some complications that came up through this evaluation. One is that matrix completion, when we're using such a simple model, may be somewhat inherently private, right? It's a very simple model. It doesn't have that many parameters. Perhaps the memorization capability is limited. There's also a lot of good theory on the uniqueness of matrix factorization, that perhaps even if a lot of data is missing, that the low rank approximation stays the same or the same upward rotation. Another one is that when we assume that the removal data is a tiny subset of all the observations, we could actually have even further speed up using Woodbury inverse. So this is a numerical trick that could be potentially faster than the vanilla alternating least square implementation. The next 2 points are very subtle but related. When we have a base model that performs really well, it actually poses difficulty for membership inference because membership inference tries to look at model output and discern the difference between these two models' different model outputs. But if both models are quite good, right, they don't have a lot of room to make mistakes. And when they don't make mistakes, they don't really have very different output. They're less likely to have different output. And that is one of the reasons that membership inference is hard on a larger scale for this type of recommendation data we're dealing with. To summarize, we propose on-trend ALS to perform exact deletion rather than approximations that may degrade the model. This method itself is extremely easy to use engineering-wise. You can use it post-training. Even though we're assuming training with alternating least squares, it's actually agnostic to any bilinear training. It just needs to be warm started by existing user and item features. It is also very fast and compute efficient rather than the common myth that unlearning is expensive. Our data removal is shown through numerical simulations to be swift, complete, and calibrated. And this concludes the third section on our methods, and I'll be taking questions here.
Thank you. I have a question about the algorithm 1 and 2 on page 31. Oh, yes, thank you. So on the right-hand side, I think the delete corresponds to PUI is 0 and block corresponds to CUI is 0.
Yes.
I was wondering if the delete part, does it have an effect on the algorithm, or is this just for privacy requirement?
Yeah.
So if we block, will it be the same?
If you just block, would it be the same? If you just block, would it be the same?
I think if you go back a few slides, maybe 27, you had your loss function. Oh yes. So if CUI is 0,
yeah.
So I was wondering if it would be the same if we preserve the original PUI.
It's possible we don't really need to do that. I didn't really look into it. Yeah.
I see. Okay, I was wondering if it was more of a privacy requirement.
Oh, I see.
Because you remove PUI from your data.
It's much okay. I think for now, it's much more likely that I could have just not done it. But I don't think it has a privacy. It achieves anything privacy specific. I do think we need to remove it from the historical data regardless. So if you assume that this whole system will just keep going, then obviously we would like to remove this part to be 0 if we're to keep the same P as we continue training. I think just putting it to 0 still doesn't quite answer the privacy question, right? It's actually quite difficult to prove privacy, as I'll talk about in the next section.
Okay, thank you.
Are there other questions? Okay, the next section is on the potential future of unlearning. I'll start by unpacking a little bit of the sensitivity issue I mentioned before. As you could see in this picture on the right, that on-training is approximating retraining very fast, but this metric is only sensitive on a pretty narrow range of a removal fraction. And sadly, this is not even a removal fraction we care about. We care about the removal fraction that is far smaller on the left, right? Which means that in most normal scenarios, it will be difficult through an empirical evaluation to even tell that there has been a change in terms of privacy. And this becomes very problematic. Another part of this is that a good initial model that performs great on everything may also perform great on any removed set, which means you always have a very good guess about the data that you have removed. As we can see on this type of recommendation data, even for really, really crazy fractions of removal, the area under curve remains fairly good, right? So all of this combined pose very difficult numerical challenges for our current membership inference setup. Now, membership inference is a really nice idea, right? We want to use classification to tell if there's some privacy loss. And we could potentially set up a set of assumptions so that we make it easier to do empirically. But overall, membership inference probably requires a major update, right? Previous researchers have shown, mostly motivated by unlearning from deep learning or like memorization in deep models, that membership inference attacks may need to be modified. We might need to abandon this whole average case scenario. It's just simply not powerful enough. And I argued furthermore, especially for bilinear models, we direly need better empirical evidence for membership inference because these bilinear models tend to be what's being deployed. And right now, we really don't have a good way to tell privacy difference. I don't want to just say, oh, look, we can't tell that there's a mistake. I know that I arrived at a model that must be different from retraining. I would like a method to show that difference. In fact, even for the method shown here on the right, it is already denoised. It's a modified version of the typical vanilla version, because typically we would like to do different data splits and take the average. If we were to do that now, that difference that we see here will completely be gone if we do any average. And one could argue, oh, maybe you just need to blow the graph way up. But remember that we're working with finite data regime. We're talking about membership inference accuracy on a particular test set. So we'll have to divide that accuracy by the number of test points, right? So this is inherently a very difficult thing to show if your difference is going to be very, very small. And this brings me to the bigger question. If we were to apply this form of unlearning in the real world, how will we even know that it succeeded? What does it mean to succeed? There's obviously the big legal question, does the right to be forgotten even apply to machine learning models? Right now, the answer is no. Even though in GDPR, it's saying that the right to erasure applies to derived data. And in many ways, the machine learning models are the derived data from users' data. But right now in the US, we don't have comprehensive privacy bills that cover this specific part. So that's a big hurdle. Next, if you were to bring forward claims, like you want to show that this platform is harming me by violating my privacy, how would I even show that? If I'm just one user, I might not be able to discover it. And can users ever prove it? Like perhaps there's some impossibility result down the line that we see that, oh, with a limited number of users, you actually can never prove it. When we request deletion, and if the platform is nice enough to accommodate for it, how do we know it has done it? How do we know that this kind of unlearning is complete? The platform could just say, I've removed your data, now please go away. And there's nothing a user could do. When we compare different unlearning methods, and this is already pretty salient in our research community, how do we know which method is better if our empirical evaluations are insufficient? Next, there's the question of governance. If one single user is not enough for showing any kind of real privacy harm, maybe we'll need a data coalition where people's data put together, where we need to have a third-party trust that I think some legal scholars in Japan are pushing for. where we want to have third-party audit, where there will be people who have access to the model and the data, and they can do their own research on it rather than relying on individual users to bring forward their claims. So I hope by now I've given you a good perspective on learning to the future, that unlearning directly needs empirical methods to show privacy loss in the first place, to show the privacy gain after unlearning, and to show the privacy difference between different scenarios and different methods. In the real world, if we want to deploy a method such as ours, we'll need buy-ins from different non-technical perspectives. And there is a legal compulsion that we need to recognize the right to erasure or rectification with respect to machine learning models. We would like to have systemic empirical evaluations to discover a privacy violation. And perhaps in the future, we need something similar to third-party audit for when individual users don't have enough information. And thank you. This concludes the last bit of my talk, and I'll be taking questions.
Thank you very much, Mimee, for the great talk. So if anyone has any questions, please, you can unmute yourself, or you can also use the chat box. So I think the last part, maybe 57, seemed very interesting. You mentioned something about Japan's current situation. Can you repeat that part?
Yeah, so I believe this is me paraphrasing their work, and I think some of them are in University of Tokyo as well. They're pushing for something based on contract theory, and that's the idea of a trust. I believe it's kind of similar to a mutual trust like people have in the States, in that perhaps senior citizens, when they enter a care facility, could sign a contract to have their data be owned by a third-party trust. And right now there's a big challenge to scale up senior care. And a lot of the data generated through medical device or other records could be used for scaling up care using machine learning based methods, but there is currently no good way to use that data. So what they're talking about is to set up a third-party trust as a way of data governance, right? So someone else will be using your data and you have entrusted your data to them. It's not specific for our definition of privacy, but it is a governance technique that could potentially solve this problem that individual users are not powerful enough against big tech companies that may have violated their privacy. Does that make sense?
Oh, I see. Okay, thank you.
Yeah, so this is very much in the works, motivated by a very different thing, but it could potentially write into law this type of data governance.
Okay.
Yeah.
So if there are any other questions. One, I often use like selling apps in my daily life, and one feature that I am suffering from is like a few months ago I bought a dishwasher, but then the selling app suddenly recommends me a lot of dishwashers, but I won't be interested in buying another dishwasher for the next few years because I already bought one. So is this kind of problem like a good application for the unlearning scenario that you talked about, or is this is it better to tackle this from another perspective?
Yeah, so I think ideas on this are numerous. What usually platforms want to develop technologies that work with, say, negative recommendation or to be less sticky, right? They want to functionally improve their model utility, not just in terms of area under curve on existing test set. They're more worried about adapting to a future where your preference may have shifted. So they're trying to anticipate the change. But what I'm talking about is that you're very aware that this advertising is caused by your previous purchase, But since you already have this device, you don't need another one. You like to just easily go and uncheck this box, and you assume that the recommendation will be back to normal again, right? And my method gives you the ability to do just that, right? You don't need to prove that I have suffered and I would like this removed. Yeah, I think a rectification, the right to rectification, will give you the power to do that. And when platforms implement something like this, it could be used for all sorts of deletion requests. It could just be like, I misclicked, it might have been a mistake, or it was accidentally trained on data that didn't belong to me, right? This is right to rectify.
I see. Okay, thank you.
Yeah, like clearly there are numerous recommendation algorithms people come up with. They're more thinking about the forward problem, where I'm talking about the backwards problem to unlearn.
I see. Okay, so I think there are no more questions. Thank you very much, Mimee, for the great talk. The algorithm and the societal issues were very interesting for me. So let's thank Mimee, and that will be the end of today's seminar. Thank you very much.